Hello, I'm Michelle Tate, the Product Marketing Manager for Oscilloscopes at Keysight. I'm very excited to introduce to you our new HD3 General Purpose Oscilloscope. Today, we'll start with an overview of HD3's key features so that you can see what all the buzz is about. Then you'll meet the R&D team who worked the past few years to bring it to life. They'll introduce to you what makes it unique in the market. We'll show real-world examples so that you can see what even the smallest signals look like on the HD3 scope, as well as hands-on demos for two key use cases: power supply testing and serial bus testing. Feel free to enter your questions in the chat and we'll answer as many as we can at the end of today's event. And of course, we'll show you the HD3 kit giveaway that you'll have a chance to win by attending today's webinar. So let's get started. With a new custom ASIC and 14-bit ADC, the HD3 provides 4 times the vertical resolution and half of the noise floor, giving you a more accurate representation of the signal you're measuring. The HD3 oscilloscope enables you to ensure product quality by debugging the smallest of signals beyond the noise in various applications, including consumer electronics, power supply testing, automotive, healthcare, and aerospace and defense. As I mentioned, we'll actually demo some of these applications later in the presentation, so stay tuned for that. But here are some examples of why high signal integrity matters in an oscilloscope. When testing power supplies, every microvolt matters. With microprocessors and microcontrollers using less and less power, the power supply levels required in the industry have moved from 5 volts a decade ago to just 0.9 volts today. And so small ripples and glitches, which were immaterial at 5 volts, can now be the source of errors that cause device crashes, reboots, and more. The HD3 helps find these glitches so that you can address them by changing the product's design as early as possible in the product development cycle. That's why engineers and QA teams need 14 bits of precision and the lowest noise floor when creating products to ensure that they can measure and see the small AC signals riding on top of the large DC signals. The HD3's low noise floor, which is less than 50 microvolts even at a full 1 GHz of bandwidth, helps ensure the signal you're trying to measure isn't hidden within the higher noise injected by other oscilloscopes. Design verification of battery-powered medical devices is another example where you need to measure signals with extreme accuracy. Using a portable oscilloscope with the highest signal integrity in the 14-bit ADC lets you zoom into the signals of interest and see waveform details more accurately. And as designs become more complex and signals smaller, engineers debugging them need to trace multiple signals at once and identify the smallest signal errors to find and correct hardware defects. To debug multiple protocols across consumer electronics, automotive, and aerospace and defense applications, you need a flexible oscilloscope that can trigger and decode on a variety of input signals. The new custom ASIC provides unparalleled speed. We introduced technology to the HD3 previously only available in our high-performance oscilloscopes. The result is 4 times the resolution and half the noise. Our custom ASIC enables you to capture elusive glitches with a fast, uncompromised waveform update rate of 1.3 million waveforms a second, which lets you see more information about your signal on the screen, all without the trade-offs in performance of other scopes in the market when you add more channels, math functions, decoding, and more. In addition to zone touch triggering, where you can draw a box with your finger on the screen to isolate signal glitches, the HD3 includes Fault Hunter software to automatically characterize your signal, hunt for errors, and save them, enabling you to quickly and easily find and debug signal errors. With 25 times more memory than our previous oscilloscopes and segmented memory, you can capture and analyze longer waveforms at a time. This is ideal for automotive and aerospace and defense applications. Plus, the new user interface enables you to get the most out of the HD3's bandwidth, up to 1 GHz, 2 or 4 analog channels, and 16 digital channels for mixed signal designs. You can use a grid to display up to 4 independent signals and control the scaling individually. Complete your debugging solution by pairing the HD3 with specialized software and probes. Application-specific software packages automate measurements and give you access to a large selection of serial bus protocols and advanced analysis like FFTs, mass testing, histograms, and Bode plots. Access a wide variety of specialized probes for quick and precise measurement accuracy. And de-risk your project with 3 years warranty and Keysight Care technical support, providing unlimited access to expertise and committed response times. And get even more out of your oscilloscope with 7-in-1 instrument integration. That's right, not only is the HD3 an oscilloscope, but it also includes a protocol analyzer, mixed signal oscilloscope to add 16 digital channels, frequency response analyzer, 100 MHz arbitrary waveform generator, 3-digit digital voltmeter, and an 8-digit counter and totalizer. And rest assured, if your testing needs change over time, the HD3 is fully upgradable. Upgrade your bandwidth, memory, and software at any time. Debug with the HD3's 14-bit ADC, providing 4 times the vertical resolution, and custom ASIC and front-end redesign, providing half the noise in a portable oscilloscope. Now let's hear from the R&D team that created the HD3. I'm excited to introduce Bob Snow, the R&D hardware project manager for this oscilloscope.
Thanks, Michelle. At the heart of the HD3 are the new custom ASICs and redesigned front end that enable engineers to get more from this oscilloscope. All the hardware elements are new for the HD3 and were designed from the ground up. The team started with a new custom front end amplifier designed to lower the noise on both 50 ohm and high impedance input paths. To enhance the measurement capability, the amplifier allows a larger gain and offset range than previous Keysight oscilloscopes, while driving the noise to levels matched only in higher performance products. The primary reason to push the noise and signal integrity capability of the oscilloscope to the limits is to take full advantage of the new 14-bit ADC, and the new ADC and memory controller systems are a result of years of developing high-performance ADCs to accurately recreate the sampled waveform. The team maintained the fastest uncompromised waveform update rate of previous products and combined it with the technology used in our higher bandwidth products to produce the signal fidelity and measurement capability of this oscilloscope. They also enhanced the memory system to offer deeper analysis of signals, allowing for more insight to find elusive issues and characterize designs. Another feature of the system is the enhanced triggering capability. In most systems, the trigger runs through a separate path, and what is displayed on the screen may be slightly different than what is in the trigger system. The new ADC for the HD3 combines the acquisition and trigger systems so that what you see on the display is what's available to use for the trigger. This provides more accuracy when searching for elusive glitches and issues. To support the new front-end ADC memory controller and memory system, the HD3 has a new processor system to provide more compute and analysis capability. Utilize this enhanced compute capability on the new higher resolution display that provides HD3 users with more viewing area for waveforms, traces, and measurements. Doug will expand on this shortly. The new HD3 hardware provides more accurate measurement and analysis of designs for characterization, debugging, and time to market while preserving your investment. Now I'd like to introduce David Sheldon. He's going to tell you about the software developed for the HD3.
Thanks, Bob. The HD3 application software consists of 3 systems, including the ASIC driver, the analysis software, and the user interface. The ASIC driver software is designed to turn on the full feature set of the ASIC. The analysis software utilizes the software from existing Infinivision products and is designed to support turning on ASIC features, taking advantage of 14-bit ADC, deep memory, and digital triggering, to name a few. Finally, the user interface software is developed using a modern GUI, giving the HD3 products a new look with no limitations on future additions. All 3 of these systems support the new custom ASIC technology. The HD3 application executes on an OS platform that has been validated in other Keysight products. The OS platform utilizes a modern OS that is equipped to keep up with evolving software, dynamic security requirements, and hardware upgrades. The OS used in the HD3 is a customized distribution designed for embedded systems and provides a platform for the HD3 application software to be flexible to meet the needs of engineers today, as well as build a path for future expansion into different areas of analysis as Keysight and customers' software needs change over time. Next, I'd like to introduce you to Doug, who architected the new user interface.
Thanks, Dave. I'm happy to share more about HD3's new user interface. We have provided a larger screen to more easily see more details of waveforms. You paid for the entire screen, so we'll let you use the entire screen. New to Infinivision, waveforms are automatically placed into separate grids, which maximizes the use of the A to D on all channels. The results area can be easily resized, and there's even a full screen mode to show nothing but waveforms on the entire screen. Check out digital channels in their own grid, which grows and shrinks to fit the number of digital channels you have on. The front panel still provides all the most important knobs and buttons. There's even a Save Screen button. The top bar provides fast access to the most important functions of the scope: channels, waveform intensity, horizontal, acquire, and trigger. Check out the plus button. This lets you turn channels on and off quickly, including math, reference, FFT, and digital. Watch me turn on an FFT with a single click. Watch me turn on and off many digital channels with a single swipe. Zone trigger is better than ever. Now you can set up to 4 zones, and each of them can have their own source. Triggering is no longer a challenge. If you can draw a box, you already know how to trigger. Finally, Fault Hunter is available on Infinivision scopes for the first time. With a single click, Fault Hunter looks for glitches, slow edges, and runts. While you get a cup of coffee, your scope can find problems in your DUT for you. Or you can even run Fault Hunter all weekend to try and find rare problems. Imagine coming in on Monday morning with a report showing exactly how that strange glitch is happening without any effort on your part. HD3's new high-resolution, large screen, intuitive user interface, and versatile triggering capabilities enable you to use the entire screen in the way that accelerates your analysis.
Thank you, Bob, David, and Doug, for that excellent walkthrough of our hardware, software, and new user interface. Now, let's see the HD3 in action. Johnny Hancock, our Keysight oscilloscope guru, will walk us through what a 14-bit ADC and low-noise floor oscilloscope gets you when it comes to viewing your signal. Later, we'll dive into how this can be applied in power supply test measurements and serial bus decoding. Let's dive right in.
Thanks, Michelle. Hi, Johnny Hancock here. Whether you're designing electronic hardware for automotive systems or consumer products, oscilloscopes are usually the go-to instrument that engineers use to begin testing. Testing often requires high-resolution measurements to verify low-level analog signals such as power supply output ripple, as well as low-level analog signals from the output of sensors. In addition, support for a broad range of embedded serial buses such as I2C, SPI, UART, CAN, and others is also important. In this short demonstration, I'd like to begin by showing you why the number of bits of conversion are important for accurate, low-level analog signal measurements. But perhaps more important, I'll show you why using a scope with a high sensitivity, low noise front end can enable you to see signal details that are often lost in the noise floor of other scopes. I'll show you these measurements on the HD3 oscilloscope. Let's get started. When engineers refer to an oscilloscope's measurement resolution, they are usually talking about the number of bits of conversion of the scope's analog to digital converter, or ADC. Not too many years ago, 8 bits was considered the industry standard. 8 bits of conversion provides 2 to the 8th power, or 256 unique levels of conversion across the dynamic range of the analog to digital converter of the oscilloscope. Each additional bit doubles the number of levels of conversion. So 9 bits provides 512 levels, 10 bits, 1024 levels, and so on. The HD3 scope provides 14 bits of analog to digital conversion. This provides over 16,000 levels of conversion. So, why is this important? Most engineers would probably say because they don't want to see a stair-step or jagged waveforms due to a limited number of bits of conversion. In other words, they want to see a smooth waveform. Let's see an example. This is a 500 millivolt peak-to-peak 200 megahertz sine wave from a low-noise signal generator. The scope is set at 100 millivolts per division. At this setting, the HD3 with 14 bits of ADC resolution provides approximately 100 microvolts of measurement resolution and shows a smooth waveform trace. Another reason why most engineers want a scope with more bits of resolution is because they don't want to see a fuzzy waveform, or waveforms that aren't thin and crisp like I just demonstrated. But truth be told, the fuzziness of waveforms that you might be familiar with is not typically due to a limited number of bits of conversion. It's usually due to the noise floor of the scope itself. What you might be seeing is random noise introduced by the oscilloscope itself, not due to a limited number of bits in the ADC. This phenomenon can usually be observed on the scope's more sensitive volts per division ranges, such as 5 millivolts per division or below. Let's now see an example of a fuzzy waveform on a scope that has lots of bits of conversion. This is now a 5 millivolt peak-to-peak 200 megahertz signal with the scope set at 1 millivolt per division. Between 500 microvolts per division and 2 millivolts per division, this scope provides 2 microvolts of ADC resolution. At this low setting, you can probably see some fuzziness to this waveform, but this is the industry best for this class of scope at such a low volts per division setting. The HD3 oscilloscope has a baseline noise level of less than 50 microvolts RMS at the scope's full 1 gigahertz bandwidth. Oscilloscope vertical resolution is not just a function of the number of bits of the ADC. It's a combination of the ADC bits plus the noise floor of the scope, which comes into play when viewing low-level signals at very low volts per division settings on the scope. So how can we improve baseline noise level of the oscilloscope to make higher resolution measurements at these more sensitive volts per division settings? One method is to use waveform averaging. This requires the input signal be repetitive, as you see here when I select averaging. Now it's thin and crisp. Another method is to decrease the bandwidth of the oscilloscope, which naturally reduces the noise level of the oscilloscope. Here you can see what this 200 megahertz sine wave looks like if I reduce the system bandwidth from the full 1 gigahertz down to 350 megahertz. Now you have less noise, less fuzziness, and now we're down to a baseline noise level of approximately 30 microvolts RMS. This is now a 20 megahertz sine wave at full bandwidth, 1 gigahertz. I'm going to reduce the bandwidth to 100 megahertz. And now the noise floor is significantly reduced, and we have a thin and crisp waveform at such a low volts per division, 1 millivolt per division. Sometimes using a lower bandwidth oscilloscope is a benefit. The HD3 oscilloscope allows you to select the bandwidth of your oscilloscope measurements anywhere from 5 megahertz all the way up to the full 1 gigahertz bandwidth of the scope, which lets you lower the noise floor of the scope down to as low as 10 microvolts RMS at the lowest bandwidth settings, giving you the flexibility to trade off bandwidth and noise for any application. Now, let's hear from Erin East, product manager of this oscilloscope. She'll demonstrate how to apply this in power supply testing.
Thanks, Johnny. Hi, everyone. I'm Erin East, product manager for our all-new HD3 oscilloscopes. I am so thrilled to talk about this exciting new technology. No matter what type of electronics you're designing or what industry you're in, we all have to measure power to some extent, whether it's characterizing every component or just measuring the output of a power supply. The combination of the 14-bit ADC and the all-new low-noise front end gives us the visibility we need to ensure accurate results from our supply. While switch-mode power supplies are the most common and efficient power supply methodology, they introduce a fair amount of noise and ripple to your signals. It's important to characterize this to ensure your device will function properly and produce an appropriate output. To be able to measure those low-level signals, you need extreme vertical accuracy. What we're looking at today is a Picotest Power Standards board, so a nice DUT to compare against as you're designing. You can see there's a switch mode power supply on this board, and I also have a switch mode power supply that Keysight makes for demonstrations. One of the key measurements we all have to make on a power supply is the amount of ripple and noise we are seeing on the output of our supply. We're ultimately testing the quality of our voltage regulation and filtering that is supposed to reject the noise from our switching component and other interference sources. It's important to verify the noise and ripple in your design are within a tolerable amount to ensure your power supply will work properly for whatever it needs to power. Bandwidth filters and a low impedance path are critical in order to decrease the amount of noise impacting your signal, so we can set those in the channel menu. You'll notice I'm using an active probe to do this measurement. Probes are often an afterthought, but the truth is your probe is just as important as the scope. It's critical to use the appropriate probe for what you're trying to measure. For my output ripple measurements, I am using our Power Rail probe on channel 1. Power Rail probes are designed specifically for analyzing the small ripple and noise riding on top of a large signal. On channel 2, I am using a 10-to-1 probe. And we can see what a significant difference that makes with the amount of noise impacting my signal. We want to use the right probe so we have the least amount of noise added to our signal as possible. Comparing these measurements on the HD3 to what I used to see on the 3000G, we can see what a huge difference this next level of vertical accuracy makes in these measurements. On the 3000G, with the same probe and scope settings, we are seeing a significantly higher RMS value than what we're seeing on the HD3. This difference in measurements is primarily driven by the front-end noise of the oscilloscope. With the lowest front-end noise, you won't see the HD3 interfering with any of these important measurements. Now, it is also even easier to detect small frequency components that may impact your switching design with our improved FFT capability. Thanks to the deeper memory of the HD3, we also have more data to work with to build out our FFT and ensure we aren't missing any frequency content. The extreme vertical accuracy is also helpful for other common power measurements, like current drain analysis and the math involved with that. The new Fault Hunter capability is also extremely helpful for finding any glitches or crosstalk interfering with something like my clock on my power supply. Here we can see it scanning a clock signal, and now we can see that it found a positive glitch. Now I can copy that to my trigger so that I'm only triggering on the glitch, and I can do some more work on characterizing that glitch and where it's coming from in my design. For those of us that only care to test what the output of our power supply looks like, the frequency response analyzer becomes an even more effective way to characterize it. To ensure our power supply will work correctly no matter what we are inputting, we can set up a Bode plot so we can sweep different inputs with varying amplitude and frequency, and we can analyze the behavior of the output of our supply with those different inputs. This is the only way to fully understand the control loop response and the power supply rejection ratio of our power supply. The Frequency Response Analyzer application uses the scope's built-in waveform generator to sweep the input, and then it plots the gain and phase in the form of a Bode plot. This is just another one of the many ways to characterize your power supply with the most accuracy on the all-new HD3 series. Now, I'll pass it back off to Michelle and Johnny for another demonstration.
Thanks, Erin. Today's electronic designs almost always include serial bus control. In almost all electronic industries, including consumer, automotive, aerospace and defense, and medical, embedded serial buses, including I2C, SPI, and UART, are utilized in designs to control and monitor subsystems.
And then there are additional serial buses found in the automotive and industrial automation industries, including the CAN and LIN buses that are used for longer distance serial communication with higher levels of fault tolerance due to the additional safety requirements in these industries. Using oscilloscopes that can decode and trigger on these embedded and automotive serial buses is imperative for most engineers working in these industries today.
I'll begin by showing a few quick demonstrations of the HD3 oscilloscope decoding and triggering on common embedded serial buses, including I2C, SPI, and UART.
I'll follow up Michelle's demonstrations with some demos of the HD3 scope capturing, decoding, and triggering on common automotive serial buses.
Here's an example of the HD3 decoding and triggering on an I2C serial bus. This is the clock signal, and this is the data signal. Below the waveforms, we can see the time-correlated decode trace. And at the bottom of the scope's display is the protocol lister table. The HD3's 7-in-1 instrument integration displays this in a similar manner to a standalone protocol analyzer. Let's look at another serial bus. This is an example of decoding and triggering on the SPI bus, sometimes called SPI. Since SPI buses have 4 digital input signals, I use this scope's digital channels to capture these signals. Scopes with both analog inputs based on high-resolution ADCs plus digital inputs with 1-bit resolution are called mixed signal oscilloscopes, or MSOs. All HD3 oscilloscopes come with the MSO capability as standard, so if you already use one of Keysight's 16 digital channel MSO cables, you get this capability for free. And finally, here's an example of decoding and triggering on UART, which stands for Universal Asynchronous Receiver Transmitter. With this serial bus, there are data lines called transmit and receive, but there isn't an explicit clock line. The clock is essentially embedded within each of the data signals based on a fixed and known baud rate. UART can be decoded in either hexadecimal format, as you see here, binary format, or ASCII. Over to you, Johnny, to demonstrate decoding of automotive serial buses with the HD3 scope.
As I mentioned earlier, there are 2 big differences between serial buses used in consumer electronics as opposed to those used in many automotive applications. One is the physical difference that serial buses must transmit and receive signals reliably. The other big difference is safety requirements. Common buses used in the automotive industry that meet these more stringent error recovery and transmission requirements include the LIN bus and CAN bus. The CAN bus has various generational variants, including Classic CAN, which has been around for almost 40 years and is still very much entrenched, CAN FD, which was first introduced about 10 years ago, and more recently, CAN XL. This is an example of the HD3 oscilloscope decoding and triggering on a classic CAN bus. So here you can see where arbitration is occurring, where the signal goes down to a lower dominant level at the beginning of the frame when the frame ID is being transmitted, and down here at the end of this particular frame, it's frame ID 211, is the acknowledge bit. Now, in the decode trace, of course, you see the frame ID, which we are triggering on this particular frame ID, 211. DLC equal 8, data link code 8, says there are going to be 8 data bytes following the DLC. And here you see the 8 data bytes, followed by the CRC, currently color-coded in blue. That means it's correct. Now, if it was red, had red font, that would indicate a CRC error. Now, if I scrunch more frames on screen by changing the time base, we can see more frames down in the protocol lister. So now it's decoding symbolically with the DBC file. The frame we were triggering on, 211, we're still triggering on that frame, but it has a name of break torque, and we could set the scope up to trigger on message names as well. We could zoom in and further and see the various signals within this frame along with signal names, transfer functions, and units. Notice some red error codes popping up. There's one. Sometimes you see them in the protocol lister. One of the error codes I know that's there is a stuff bit error. Let's now set the scope up to trigger on a stuff bit error. go in you, change from triggering on a frame ID, and down here you can see the various error conditions we can trigger on, including error frame, acknowledge error, form bit, stuff bit, and CRC field error. The scope can also be set up to trigger on specific bus errors. Let's stuff bit, and there it has triggered on a stuff bit error. If I zoom in and take a close look, this is a stuff bit error. It was at a recessive high level for 6-bit periods. The maximum allowed in CAN is 5-bit periods. The HD3 oscilloscope also supports triggering on and decoding the newer CAN FD bus, as you see here. FD stands for flexible data, which means that more data bytes can be transmitted during each frame, up to 64 bytes, and at a faster bit rate, up to 8 megabits per second versus just 1 megabit per second with classic CAN. Here you can see the arbitration field, which in this case is being transmitted at 500 kilobits per second, followed by the data phase, in this case 64 bytes transmitted at 8 megabits per second. So you can pack more data into a single frame running at a faster rate to reduce overall bus load. The most recent variant of the CAN bus is called CAN XL, which stands for extended length. The HD3 also supports this more recent and more robust version of the CAN bus. As you just saw in these demos by Michelle and myself, the HD3 supports triggering and decoding on a broad range of serial buses for a variety of applications to speed your debugging. Now back to Michelle.
Thank you, Johnny and Aaron, for those great demonstrations. I hope you all enjoyed seeing the HD3 oscilloscope in action and how our custom ASIC and 14-bit ADC enable you to debug with 4 times the resolution and half the noise floor in a variety of industries. These demos are just the start of diving into our new oscilloscope, so I've included additional product information in the handouts on your screen. If you want to discuss your specific application, please fill out the survey appearing on your screen and visit keysight.com/find/HD3 to learn more. Now let's jump into the Q&A, where Daniel's live here at the Keysight Scopes HQ.
Colorado Springs. I'm Daniel Bogdanoff, a test geek here at Keysight, and I'm joined by Aaron, who you saw earlier, the product manager for the HD3. We have your chat pulled up, and we've been enjoying watching these come through, and we're going to take your questions live now. So, Aaron, first off, thanks for being here.
Yeah, thanks for having me. I'm excited to be here, finally
How-
talk about the HD3.
How excited are you for the scope, and how long have you maybe been working on this behind?
Oh my gosh. Myself, maybe a year and a half, but of course the team has been working many years on this now.
Yeah.
So the whole team's really excited for this to finally be out.
Absolutely.
Yeah.
And we have a bunch of the team in chat too. They've been responding to some of your questions. But we're going to take questions from the chat. I have it pulled up, so we're going to watch them coming live. Good to see everyone saying hi. First one is from Sifula in Germany. It says, are the math functions also based on 14 bits of resolution?
Yes, the math functions are also based on 14 bits of resolution. So as Doug had mentioned in the user interface section, we have the split grids. Those can be used between the different channels and also the math capabilities. So you can use the math functions on each grid as well and get that full 14 bits for those math functions.
Yeah, I think one of the things that really surprised me when the scope came out was when I first got my hands on it was like the split grid display. I was like, whoa!
Yeah.
Felt like I was using a much higher end scope, because that's what I expect from those.
For sure, yeah.
Very exciting. Next question we got from Christoph. Is there a free software to capture the screen of the scope when connecting to the oscilloscope, or the computer with like, how does the, maybe talk through some of the capture mechanisms?
Yeah, so there's definitely a few different ways to capture things on here. We can, of course, connect our USB right to the front of the oscilloscope. There is a screen capture button on here. And then if we go into the front panel, there's file and save section, and you can determine exactly where things save there. Also, if you connect on the back of the oscilloscope, there's an Ethernet connection. You can connect it over LAN and actually pull up the screen of the scope on your computer and take screen captures that way as well.
Awesome. Yeah, so just like our other scopes in this space, we have kind of the VNC server at the back, so you can do it just right out of your browser too. And that's kind of my preferred way, because I usually just have my scope on my bench with the LAN hooked up, and I can just bookmark my scope and pop it up. It's great.
Exactly. And just actually slight difference there. Instead of opening your browser, you do have to use a VNC application. So you use a VNC application, just plug in the Ethernet, or excuse me, the IP address, and you have the scope screen ready to go.
Yes.
Yeah.
Thank you for clarifying. The next question someone asked is, how did you get the noise so low? That's kind of a big question.
I don't know if I'm the right person to ask for that, because I didn't get the noise low, but I know that the R&D team worked really hard to leverage our advanced technology from the UXR series and our high performance oscilloscopes, leverage that advanced and very precise front end into these lower bandwidths, so that we do get that really low noise front end, even at these lower bandwidths.
Yeah, there was a lot of discussion up front when the original 14-bit ADC spec leaked, like on the EV blog forums and sorts of places like that, where they were like, oh, they're using this ADC from this company. It's like, nope, we designed the whole thing ourselves. And that's, you know, some of the team here just on the other side of this wall really specializes in making these ADCs sing. So, and yeah, go ahead.
The new 14-bit ADC actually isn't even in our high performance oscilloscopes.
Right.
It's only in this HD3 series.
And the chip is not just an ADC, there's more to it. Can you kind of expand on that a little bit?
Yeah, so we have the ADC itself, which is custom designed by Keysight, and then we also have the ASIC as well, which the ADC actually sits inside of. So we have a completely new customized ASIC. It is nothing like the ASIC that was in our previous Infinivision oscilloscopes. It is the MegaZoom 5, as it is the next generation of MegaZoom. We previously had the MegaZoom 4 in our X series. So MegaZoom 5, all new technology. We do have an individual ASIC and ADC per channel in the oscilloscope now as well, which is very new for this level of scope.
And Timo just asked if there was a license for connecting to the scope. No, that's just a thing you can do with the scope, like out of the box. Yep.
Yes.
Next question asked about isolation between channels. Can you talk a little bit? And Bob, the R&D manager who you saw earlier in chat, said there was 100-to-1 or greater than 100-to-1 isolation, which is pretty solid. Can you talk a little bit about isolated channels and kind of what that might?
Yeah, I know that since there's no interleaving between these channels, and like I was just saying, there are components dedicated for each of the channel paths. Everything is isolated for each of the channels. So there's not that interleaving or interference with each other, and they're not sharing specifications or components in there.
Awesome. And someone asked if we're hiring. Probably. Yeah, jobs.keysight.com.
Yeah, I'm sure there's something open. Yeah,
there's a lot of us here. Can you talk a little bit, one of the questions we saw and see a lot was, how does the scope handle complex signal environments and noise reduction?
Yeah, good question. So I guess a few different ways to answer that. So noise reduction, one of the biggest things is we want to make sure we're using the right probe. If you're trying to do a really low noise measurement, you want to make sure your probe is not introducing noise as well. So in this specific case, I just have a passive probe connected. Passive probes introduce a lot of noise. So if you're trying to make really low level measurements, maybe on a power rail, you want to use a probe that's customized to not add noise at those really low levels. So when you're making those millivolt level measurements, you don't have that added noise from the probe either. So making sure you're using that right probe, and then also using the low impedance path as well. By default, we're on the 1 mega ohm path. And then we want to be using that 50 ohm path to make sure there's the least amount of noise interfering with our signals that we're inputting there. And then The other question around that was isolating complex signals. I just want to also show quickly the zone trigger capability. I'm just going to bring up a built-in signal here, but we can actually just draw a box on the screen and isolate that specific part of the signal. So I can use the combination of those different settings on the scope and my probing to make sure I'm injecting the least amount of noise, and then some of those cool capabilities like zone trigger to isolate that really complex signal.
Yeah.
Yeah.
Awesome. I mean, who doesn't love zone trigger, right? I
It's the
remember when I first started at Keysight, I saw a zone trigger demo. We were just releasing the 4000X series scope, and we had some folks in, and someone did it. My mind was just absolutely blown by that, and that feeling of awe has kind of stuck with me almost
For
every day
sure.
since I've been here.
Yeah, even people who've been using zone trigger forever still just love zone trigger. It's one of the coolest features. And just to talk about that really quickly, compared to what we had on our X series oscilloscopes, on the HD3, we now have 4 different zones to work with. Let's see if I can get them to pop up here. We have 4 different zones to work with. We can work between the different channels here now. We have different logic we can use between them. So much more enhanced zone interface as well.
Awesome. A couple questions. People kept asking if it was Windows or Linux. I don't know if we're allowed to say we base it on Linux, but we base it on.
Yes, we're allowed to say it's in the data sheet. So yeah.
Good. Yeah.
Yes.
There was some debate in the chat about whether we'd actually said it or not.
Yes,
I'm just gonna say it. It's based on Linux.
Yes.
Yeah. Back in the day, they were Windows based, but we made some changes and it got it on Linux, and that seems to be a really good platform for us for these going forward.
Yeah.
We also got some questions around the giveaways, so let's see if we can get a close-up on this guy. We are giving away, I think, like 170 of these. We're calling them assembly brick kits. So they are like not fully functional oscilloscopes, obviously, but they are a fantastic, like everyone who sees one of these, we've been like having employees asking us like, hey, where do I buy myself one of these? Because they're super fun. So this one's a prototype, but if you are here today, so if you show up for the live stream, or I believe on demand, as long as you logged in and watched at some point, you will be in the draw for these. We're giving away, I think it was 173 or 8, something like
178.
177. It's a lot. So we'll shoot you an email in the next like few days if you are a winner of one of these. So these are awesome.
They're so
I can't believe it happened. They're so fun.
I know.
So that's the deal with these. We are giving those away today. Other questions we got. This was just a simple one. How does the HD3 oscilloscope differ from the previous models?
Yeah, good question. So I would say the instruments or models that it's largely meant to kind of replace. It's not going to be discontinuing them or anything, but the models it's really meant to replace over time are the 3000, 4000 X series space. So that's the 3000A, T, G, and the 4000A and 4000G. So just in terms of bandwidth, capabilities, pricing, that's all kind of where it sits in the InfiniVision family. The big difference, though, is, of course, around those specifications we keep talking about, the 14 bits, the extremely low noise, the all-new ASIC. It really is completely new hardware, all new technology inside here. Nothing was brought over from the X series. It is all new. So leveraged as what we could from the high performance side, but largely it's made of brand new components as well in there.
And then we got a question from Sergey Popotov, the Bodhi plot. And I know we talked before, we're running some prototype code here, so we don't want to do that one live today, but can you talk a little bit about that capability?
Yeah, definitely. And I can definitely bring it up on the screen here at least. I don't have any device connected, so I won't actually run the test here, but we do have that frequency response analysis capability. See if I can get my finger. We do have some frequency response analysis capability in here. It's very similar to what was on our X series oscilloscopes. It utilizes the built-in waveform generator on the back of the scope as the input. Just give it a second.
Prototype code on
As an input to our device. So it will measure the input on channel 1 and the output on channel 2, and then it will plot that Bode plot on the screen there.
And I think it's turning off because we're not fully hooked up like we should be.
Yeah, yeah.
Realizing something's wrong.
Yeah, definitely. So I'll press run analysis just because we'll see it pop up. I won't actually run it here, but we can see it actually starts plotting the Bode and phase down in the bottom here. We can see, I'm going to press cancel, we can see that it's trying to do the source on the top and the output in channel 2. So it does utilize the built-in waveform generator for that. The frequency response analyzer is standard on the oscilloscope by default, and you do not have to have the WaveGen license to use the Bode plotting. You can use it without the WaveGen license.
Yeah, and it's another killer one that we saw. Someone asked if we can connect a mouse to it. Yes. Marco asked what type of touchscreen it is. Touchscreen, so none of that resistive touchscreen nonsense.
And we do have the multi-touch capability now as well, so you can switch between the zone mode up here or the multi-touch, and you can actually do the pinch zoom on your waveforms now, both horizontal and vertical.
Yep. Someone asked also, is it like a power brick or an AC? It's just a straight AC connection. It has kind of that, I forget the name of it, but that standard power connection. And you can, I think the transformers we use, you can use like in Europe or in the USA. It does the 220 and the 110.
Exactly, yes, correct. So, you just have to have the right power cord, but yep.
Yep, so no power bricks here. So Jeff Wienkrat asked, is the UI navigable by touchscreen only, or do the physical controls also control the UI? So can you talk about maybe some options through using this UI? Because there's a lot it can do.
Yeah, there's definitely a few different ways to do everything in the oscilloscope, whether it's turning on sources or different measurements. So you can use the front panel here. We see the different channel buttons. You can do a lot of things through the front panel. But to turn on some of the more advanced capabilities like frequency response analysis or the Fault Hunter application, you want to open up this menu over here and go into the Analyze menu. So I would say it's very much a combination of the touchscreen and the buttons. You can, of course, use a mouse if you want to have the touchscreen disabled. And you can also touch these buttons up here and around different things on the actual screen of the scope as well. So there's a few different things, different ways to navigate everything on the scope.
And it's always a debate both internally and externally of like, what buttons exist on the scope? What do we handle in like soft keys? And I think we're at a point in time where we like have the processing power, we have the expectation of touchscreen control, where we've gone more in the direction of like our higher end oscilloscopes, which have some basic knobs and buttons, but most of it's driven through the screen or through a mouse. And you saw Doug back earlier. He's like our UX whiz who's the brains behind this UX operation. And there's so many just really exciting things. It's even like the ability to do this sort of windowing adjustment it's like things you expect a normal interface to do now. It does really well, but that's not always the case for oscilloscopes. Is having a chance to take a scope design UX refreshed from the ground up is just a really refreshing thing.
Definitely. And just while Daniel's looking at questions there, I just want to also show this little plus button up here. That's a way for us to turn on some of our different sources. Now. I can also go into custom layout right here, and I can either do vertical where they're stacked on top of each other, horizontal, and I can actually drag around all the different sources, including that gain and phase from my Bode plot I just had going on, to where I want them to show on the screen. And you can save those setups of the display so you can recall them for those specific tests you're doing. And Doug had also mentioned the full screen mode that's right down here. I can either full screen the results or the waveform. I'm going to do the waveform, so we actually get the entire screen taken up by our waveforms.
Yeah, there was some unbelievers on full screen mode when this thing was coming out. But I remember when we were doing our internal launch, so many people came up and were like, I didn't like full screen mode for a moment, but as soon as I started using it, it just made so much sense.
Yeah.
So give that one a try if you're a little questionable on it.
Yeah.
Like,
once you
give it a whirl.
have the test set up and you're ready to do that analysis, it's definitely nice to have that extra room.
There was some question Francisco was asking about the FFT.
Yeah.
Are you up for doing a little FFT demo?
Yes,
we didn't plan it, but
I can try my best here. Yeah, I'm just going to go ahead and do an FFT just right off of channel 2 here, or one of the channels that doesn't have something plugged in here, just to show that low noise floor that we were looking at in the recorded show before this. So let me just turn on channel 2, and the settings we're really using to kind of compare to the competition in terms of noise floor are 2 millivolts per division, 50 ohm, and I'll just go ahead and I'm going to analyze FFT, and I'll set my FFT to channel 2, and I'll go ahead and turn that on. I'm usually driving the scope from that side of the screen, I've realized. So we'll just go from, we'll go all the way to 1 gigahertz actually. So I just want to show the full bandwidth of the scope, show that flat response across the entire thing there.
So one of the things you look for when you're looking at something like this with FFTs, if you're unfamiliar, is in a noisy system or a system with an ADC that has some like jitter and like some leaving errors, you'll see these spikes show up in the noise floor. What you want is basically a flat top, almost like a flat top haircut, where you want the top to be good. What happens down low matters less than the spurious free dynamic range. So basically, how much dynamic range do you have between your maximum and your minimum without a spur sticking up and getting in the way? So by showing something like this with nothing connected, it's not even like grounded. I guess we could probably ground it and that might do something. But you can really get a good feel for how good the noise is on this scope. And FFT is just a really quick and easy way to do this. If you have a scope on your desk, try it out, see what it looks like. It kind of, every vendor and model, it looks slightly different, and it's a good thing to know about your scope.
Yep, definitely. And you can set it up just the exact way I did on every oscilloscope and have the same settings. Always make sure you're at that same either 2 millivolts per division, 50 ohm. Just make sure you have the same volts per division and impedance setting on all of your oscilloscopes that you're comparing. But we can see here, we are picking up a little bit of interference in the studio. We got a lot of things running right now.
So many
We're
LED lights.
minus 104 dBm. Our closest competitors minus like 88 dBm. And then we can see the AC RMS is at 49 microvolts RMS. So just a nice way to use the FFT to show that off. I'll try to set up a small tone.
Yeah.
Yeah?
Do that. And I'll talk about dBm and RF measurements.
All right.
One of the things you look for RF also, and those of you who have been in the RF space know this, when we get to RF, we talk about dB because everything's measured on a log scale instead of a linear scale. So I'm not going to go into what a log scale is, but dBm is so dB is basically a ratio of power on a log scale. So like 1 dB to do a 1 dB gain is like a 10x on something else. Or if you have power, then you're at like a log 20 based system instead of a log 10 based system. And then dBm is with respect to power. So anytime you hear dBm, that means power. Anytime you hear dB, that is just a reference to something else. So it'll be like an increase from one level to another. But dBm is based on like watts, and I don't remember the specific conversions, but I think I stalled long enough for you to be ready.
I'm ready. I'm ready. Good job. So yeah, I also just wanted to show what that really low noise floor on the FFT actually gives us. So we can see I'm producing a really small tone from my waveform generator on the oscilloscope using a 60 dB attenuator. Maybe somebody in the chat can do the math for me on that, what that equates to. I'm doing a 20 millivolt peak-to-peak signal through that 60 dB attenuation, and we can see that very clearly on our FFT here. So we can see that's about a minus 90 dBm peak. That's well into the noise floor of other oscilloscopes in this class. So we're able to see those really low level peaks clearly that could be causing interference or issues in our design.
And people are doing the math in chat, which makes me very happy.
I know somebody would.
Everything I expected. Where else are you going to get this kind of entertainment? Do RF math in the chat. Someone else asked, Inaki Castillo, the top frequency of the waveform generator, because these are pretty significantly upgraded from our last one.
Yeah, definitely. Good question there. I hadn't talked about that yet. So the waveform generator we used to have was 20 megahertz. Now it's 100 megahertz in here. So we have a 100 megahertz waveform generator, and we also have a 16-bit digital to analog converter in that waveform generator as well, which is significantly improved from what we had previously. So you have a much more enhanced output there.
Awesome. Someone asked how much waveform can it generate? So I think that's what the question is.
Hopefully that answers it.
Some questions about, let's see. Oh, there's some corrections on the math. We're almost out of time, so we'll take like one more thing. Do you have, you've been demoing this in front of people all over the world for the last 6 or 8 months.
Yeah.
Do you have a favorite demo that you like to show when you do this?
Oh, yes, I
walk us
do.
through?
By far, yeah. Let me just go for a default setup really quick, which you should always do before every test.
And that
I'm
resets the
going to-
waveform, the screen grids and everything based on what's...
Exactly. Resets all the settings so that it kicked it back into the 1 mega ohm impedance, the original volts per division. So I'm going to use the demo mode of this just to pull up a signal here. But my favorite thing in the oscilloscope is Fault Hunter. It is so cool. If you have a signal where you see there's a bunch of messy faults going on and you want to pull them out, or if you have a signal that looks clean and you want to run Fault Hunter on it over the weekend, it will pick up those infrequent events. So it's going to run here for just a second, and then we'll see how we can actually use the copy to trigger functionality. So Fault Hunter basically does a bunch of fancy mask tests in the background. That's what the application is. And it looks for all of these different tests that we've specified: positive glitch, negative glitch, slow rising edge. And I had it so it just auto set these different parameters, but the parameters for each of those tests are also definable by you as well. So it will tell us if it failed or passed those tests. If I look in the background here, I can see my original messy signal. We're still on that default edge trigger. I can see there's some runts and some timing jitter going on here. My signal's shifting around. If I pull up the trigger menu, we can see it's still on that edge trigger. So if I go back to Fault Hunter, we can see it did detect a bunch of faults. If I just press copy to trigger for one of those, it actually changes the trigger conditions automatically to what's required to show that specific fault. So that's just one of the coolest things that I think is on this oscilloscope to help speed up testing and then also help detect those infrequent events.
Awesome. There are some questions on the origin of the name Fault Hunter, and Mike Hoffman, shout out, came in and said Doug Beck fought for that name. So you can thank Doug for the name Fault Hunter. It's a pretty...
This is definitely Doug's pride and joy as well.
And it does like machine learning on the signals and then figures out what's weird. It's like, it's when it
really
first
cool.
came out, it's like, whoa, this is kind of the future.
Yeah. And it's something we had on our MXR, EXR series scopes. I just think it's even better in this kind of level of oscilloscope where we're all really doing that general debugging. But yeah, we should see a lot of cool things coming for Fault Hunter in the future.
And yes, Vlad, the MSO channels are in the back along with the WaveGen output and some of those other things. But we are out of time. So thank you so much for being here. Remember, if you showed up today or you're watching this on demand, you are in the drawing for these brick kit winners. We'll shoot you an email if you won those. There's also a survey on your screen, so please fill out that survey. That helps us make these events better. And then if you want to learn more about the HD3, go to keysight.com/find/HD3. Erin, thank you so much for being here today.
Thank you, Daniel.
And I'm Daniel Bogdanoff, and on behalf of the whole Keysight team, thanks for being here, and we'll see you next time.
Thanks, everyone.